Okay, so the plan for today is to finish the last little bit of 3-3 measures of position and start chapter 4 probability, but we have a lot of additional administrative things to chat about really quickly here. So the main thing is the Unit 1 exam on chapters 1 through 3 is next week or this coming week, however you want to say it, this coming Monday through the following Sunday, it will be available. So it'll be available on Monday. Let's see, what date is that? I want my little calendar pop up here. Um, Windows like refuses to open my calendar. So let me get the date for you just so that I don't say it wrong. Because I know if I try to add, I'll say it wrong. Okay, Monday the 30th through what is that? October the 6th. So those are the dates the exam will be available. I'll post an announcement that'll have a lot more details about the exam and how it works and all of that. Oh, now it decided to open up. Just running a little slowly. There we go. Windows, the usual Windows craziness. So where was it? Okay, so next Monday at 9 a.m. through the following Sunday at 11:59 p.m. The exam will be available. You can take it anytime you want during that time window, and the material will be chapters 1 through 3. I'll have a sample exam posted this week. I should have it posted this afternoon. I have the exam and sample exam written. I just have to go back through and just kind of look through everything, make sure that I'm happy with everything before I push out the sample exam and make that available, and then get the actual exam kind of set up with the dates and times and all that. As a general rule, we will use ProctorU for proctoring. However, for this first exam, a couple of my faculty members have reached out to me and they've had a little bit of tech difficulties, not super super big difficulties, but they've had a little bit of challenges with getting ProctorU to work properly. And this is our first semester switching from Examity, which we used to use, to this new system, ProctorU. So that's just made me a little bit wary about making that available for this first exam. So I want to reach out to one of our support folks, make sure that we get all that cleared up, and then we'll plan to have ProctorU up and running for the Unit 2 exam and for the final exam. So no ProctorU for the first exam. You can just log into the exam essentially as though you were logging into a homework. It won't be password protected or anything like that. You can sit down and take it. It will be timed. But again, more information on the timing and the sample exam setup and all that, the dates and all of that in the announcement that's coming out. Can I share a link to the videos? The videos were not included in the email. Yeah, let me see. Yeah, maybe I can just post them in there. Um, I probably can just make this available longer. Let me try that. So let's start there. I'll just make this available through the 29th. It might email you again, but if it does, then you kind of know to expect it. So let's start with that. All right, now that should be available. Yeah, I apologize for having to cancel a class on Monday. It was as a department head, I have to do classroom observations for my faculty, and that's actually a really important part of their feedback and them getting tenure and all of that. So, and that was really the only time that we could make that work. All right, let me see if I can. Sorry for the uh, diversion. Let me see if I can just paste this into the chat. Okay, that did not paste properly. All right. Well, yeah, it's not coming over into the chat super nicely, and unfortunately, Blackboard likes to turn links into these little windows, which makes it a little hard to copy things over. So, um, but check back on Blackboard. I've made the announcement available for longer. So if you weren't able to watch those videos, the idea was that you would watch those two videos during class time on Monday. But if if that didn't work for you, if you had to kind of miss that time for some reason, you should be able to see the two videos now along with the relevant timestamps. If you haven't watched those two videos, what we do today might not make a ton of sense. So you might also need to come back and kind of review the recording for today. Um, yeah, so uh, let me fix my window over here. Okay, so yeah, so those links are available on Blackboard. That's about the best I can do at the moment, but if you're still not able to get to them on the Blackboard site, if for whatever reason the links aren't working, um, then reach out to me and I can grab the links off of YouTube again and send them to you along with those timestamps. Um, yeah, so sorry about having to cancel on Monday, but that was really the only time that we were able to make my schedule, the dean's schedule, and the faculty member schedule all kind of mesh somewhat. So, and the dean's schedule is much more restrictive than mine. So, uh, yeah. So anyway, so yeah, back to the exam. Uh, like I said, I have the sample exam and the exam created, but I just want to go back through, it's always good to kind of do something one day and then sleep on it, come back the next day, sometimes catch, minor errors, that kind of thing. So I'm going to check over it today. Should have the sample exam posted and available this afternoon. Note also that you'll be allowed to use a formula sheet on exam one. The exam one formula sheet is posted in the supplemental materials folder on Blackboard. So check out the supplemental materials folder. I've also posted a couple other things, the chapter 4 PowerPoints. There are three different PowerPoints, three parts for chapter 4, as well as some programming examples, particularly for the box plot. And I might post a couple extras after today. I know there were some folks who were interested in, IT and programming, that kind of thing in the course. So, so that this should give you some different examples. I think I have examples in MATLAB, which is kind of a scientific programming language, Python, and in the Jupyter notebook where it's kind of like Python, but like on the web. So I think those are the three I have for the box plot. Um, so if you're interested in that, you can feel free to look at those and track along. But that's not something that's expected for the course. I want to make that very clear. You definitely don't need to know Python or MATLAB or something for the course. This is just something extra that if you're interested, if that's something you find interesting and you want to pursue, uh, you're certainly free to do that. But if you're like, no, that's not what I'm interested in, then any of the box plots we would need to make for the class, we can just make them by hand. So that's perfectly okay. Do we need to be able to use Excel for exam one? Um, it depends. The problems that I choose for the exam won't be ones where, for a mean, there will be more than say, 10 or 15 data points, or for a standard deviation, more than like 5 or 7 or so. So, I wouldn't intentionally put a problem on there that you would need to use Excel for. That being said, you might find that, say, to compute a standard deviation, it's going to be easier to use Excel than to go through it by hand, and you're welcome to use Excel if you want. If you prefer to do it by hand using a, calculator TI-83, something like that, doing the calculations, punching it in, getting the answer that way, you're certainly free to do that as well, and you should be able to do that for the exam. There are problems on the homeworks, typically maybe 2, maybe 3 problems in each of the sections in chapter 3, or well, 3.1 and 3.2, I suppose. A few problems near the end of the sections that are a little bit lengthier and do really, cross the threshold into where I really would strongly recommend using Excel. Doing them by hand would be overly cumbersome, take a very long time, and frankly, you'd probably make an error somewhere along the way. I would probably make an error somewhere along the way, just making a silly decimal mistake or, adding them together, or just forgetting to add one in the calculator, something like that. Um, Super important, there are no due date extensions on exams. So because the exam is open for basically a full week, you should be able to find a time in there that works for you to take the exam. So don't wait until the last minute to take the exam. I would strongly recommend planning to take the exam on or before Thursday night. It's through Sunday night, but if you plan to take it on or before Thursday night, if something happens, power outage, a personal thing comes up, you have a good bit of buffer. If there's a tech issue, if something's not working with your WebAssign or whatever, you have a full business day to get in touch with me. I can reach out to the reps if we need to have something fixed from their end. You can reach out to Cengage tech support or CCAC's IT folks. All of that is available to you. If you wait until, Sunday at 7 p.m., most of that's not available to you. So definitely plan to take the exam earlier rather than later. Trying to squeeze out another day or two of studying is probably the benefit of that probably isn't worth the risk of potentially having, an unexpected problem pop up and then not being able to take the exam and getting a 0 for it. Yeah, so I'll post more about the exam in the announcement. I just wanted to let you guys know about the exam, but yes, it has to be, roughly speaking, it has to be completed in one session. So once you start it, the timer starts counting down. Now, uh, if you log in and get half an hour into it, and then your internet connection, something happens to it and it logs you out, you can log back in and pick up where you left off. Um, but you can't say like do a half an hour today and then like wait till tomorrow and then do another half an hour or something. That's not going to work. So roughly speaking, yes, it has to be completed in one session. But if you get booted out for some reason, some tech issue, you can log in and pick up where you left off. But you know, the timer does continue ticking. If I also haven't decided 100% on what the length of the exam will be, probably an hour. But if you started the exam at 10:30 a.m. on Tuesday, like it's going to be submitted at 11:30 a.m. on Tuesday. So you can't come back and then complete it at a later time, but you can log back in if you need to. Yeah, I mean, I'm not going to go through all the details of the exam. That's what I mentioned a couple of times now is I'm going to send out an announcement with all the details, but I wanted to hit the high points, and then just read through the announcement when that comes out. So like I already said a couple of times, the exam and the sample exam aren't finalized, so I'm finalizing those before I get the details sent out. Okay, so I think that's probably all the time that I want to spend talking about the exam. We've already gone a little more in depth than I had planned to with that. But again, keep an eye out for the announcement. That'll come out through Blackboard, copied to your email, and the sample exam should be available probably this afternoon, and the announcement will reflect that. And then just we mentioned this already in response to the question in chat, but so again, last time Monday's class was canceled, but I assigned those videos to watch. So if you haven't watched them, make sure that you go through and watch them. And then we're gonna actually do a really quick review of that material before we jump into the first topic that was not covered in that, the 1.5 IQR method for identifying outliers. And the quote of the day today is that difficulty tends to increase non-linearly with complexity. If you make something, twice as complex, it's probably going to be more than twice as difficult. So if we're looking at solving a math problem or a stats problem or something like that, we want to look for ways to decrease complexity before we increase it. One example is if we have a linear equation that has a bunch of parentheses in it and stuff, we want to simplify both sides before we start applying equation solving steps. We want to reduce complexity before we do something that increases it. and then reduce again before we increase it again. We always want to try to reduce complexity as much as possible before we increase it. If we kind of increase it a bunch and then get to this big peak and then try to reduce from there, it's going to be quite complex, quite difficult um, to simplify again. Okay, I'm gonna this crash course on 3.3. So just in case you haven't seen the videos, this will give you a basic idea of what's covered, but definitely this isn't going to go into it as much depth as the videos. If you have questions along the way, feel free to ask. But if you haven't watched the videos yet, this might not make as much sense. So I definitely recommend going back and watching the videos if you haven't done that yet. Okay, so 3.3 measures the position or measures of relative standing. What is the basic idea? We're deviating from 3.1 and 3.2 a little bit here. 3.1 and 3.2, the idea was we want to describe an entire data set with one number, or really some aspect of an entire data set with one number. Maybe we want to say what's the typical data point in this data set. Maybe I report the mean, maybe I report the median for that. Or I want to say how variable is the data set. Maybe I report the range, maybe I report the standard deviation, maybe I report the coefficient of variation, one number describing some characteristic of the entire data set. 3.3, we're switching gears a little bit. We want to describe the relative standing, the position of a certain data point with respect to the rest of the data set, with respect to all of its neighboring data points. And we could say one data point, so it could be a specific point in the data set. We could even say one data value or one potential data value. A lot of these we can talk about a potential data value that might not be a member of the data set as we have it now, and we could still answer a similar question. But the position of one data point, one data value, or one potential data value relative to the other data points. So one such measure is the z-score. If x is the data value that we're interested in, if we look at x minus mu over sigma, take the data value we're interested in, subtract off the mean, and divide by the standard deviation, we can interpret this as the number of standard deviations above the mean that x is. X is z standard deviations above the mean, and we interpret a negative z-score to mean below. So if we're negative 2 standard deviations above the mean, that means we're 2 standard deviations below the mean. A couple important notes. This is a unitless quantity. Of course, my data value or potential data value is in units of the original data, as is my mean. So this numerator is in units of original data. And we took some care in section 2 to develop a measure of the standard deviation that also was in units of the original data. The variance was in units of, or square units of the original data, but the standard deviation is back to original units. So our units divide out. We have a unitless quantity in the z-score. That's very nice. We saw, for instance, with coefficient of variation, that was another unitless quantity that made it a little easier to compare things, maybe between data sets. At this point, the z-score, it's, kind of maybe a somewhat interesting measure, but it'll actually become very important starting in chapter 6. Once we get, say, halfway through or so chapter 6, more or less from that point on in the course, we'll use the z-score idea on almost every problem. So certainly for chapter 6, 7, and 8, we use the z-score explicitly or some close variant of it on essentially every problem that we do. So it becomes very important starting in chapter 6. We'll see it come back. So for instance, if I was maybe looking at the Brandon data, and if I was interested in finding the z-score, for, well, I could pick one of these data points for like 5 returns per day, but I could even pick a hypothetical potential data value, maybe like 6 returns per day, even though Brandon never actually achieved 6 returns per day. I could still ask the question, what would be the z-score for a data value 6 returns per day? And that will be 6 minus the mean of 8, which we've calculated in the past, over Brandon's standard deviation of 4. That's -2/4, or -1/2. In other words, the data value 6 would lie a half a standard deviation below the mean in the Brandon data. And we could go through several examples. There's more examples, of course, in the videos where we talk about this more extensively. This is just a quick run through of these ideas. So z-score, very important, starting in chapter 6. Kind of a nice idea. It's unitless. It tells us the number of standard deviations above the mean that our data value is. If z is positive, we're above the mean. If z is negative, we're below the mean. And that's probably about all that we need to say right now. So percentiles, what's the idea of a percentile? If I say that a data value x is at, say, the pth percentile, what do I mean by that? I mean, roughly speaking, that p% of the data points have a value less than x, and 100 minus p% of the data points have a value bigger than x. So if I say that this score on an exam is at the 70th percentile, I mean, that person did better than 70% of folks who took that exam and worse than 30% of folks who took that exam. So if you're at the 99th percentile, that's really good. If you're at the 2nd percentile, that's not so good. Be a little bit careful, because if you're at the 99th percentile, that kind of means you're in the top 1%. Or if you're like at the 3rd percentile, you're in the top 97%. So you have to be a little bit careful with the precise wording. So you want to be in the top small amount of percent, the top 5%, the top 3%, that's usually good. Or you want to be at, say, the 97th or the 99th percentile, something like that. Most of the time you don't want to be in like the top 90%. That means 90% of people did better than you. And you don't want to be at, say, the 10th percentile most of the time. Okay, so how do we compute percentiles? Well, let's take the Ashley data. Oh, and it doesn't matter whether it's a population or a sample, we do it the same way. I see I have 5 data points. And what I want to do is I want to allocate the chunk of the real line from 0% to 100%, or from 0 to 1. I want to allocate equal sized chunks in that interval to each of my data points. So 0 to 1, or 100%. I want to split this into 5 equal sized intervals. So I need 4 tick marks. I need to cut it 4 times in the middle to make 5 bins. I note that 0 is 0/5 and 100% is 5/5. Each of these tick marks is just going to tick up 1/5. 1/5, 2/5, 3/5, and 4/5. Or these will be at 20%, 40%, 60, and 80%. These are all percents up here. Now I'm doing this graphically. Any of the problems that we do, we'll be able to do graphically. We're going to pick problems with a small enough n that we can write this out reasonably. If I had n of like 75, I would not want to write all of this out. But we're focusing on doing this graphically, so it's a little easier to understand what's going on. The book has an algorithmic approach, like you do this computation and if the number comes up this way, you do this. If it comes up this other way, you do that. I think that's a little bit more than what we need. Then I start with my data point with the lowest value. I put its value in the first bin, take the next data point with the next lowest value into the second bin, and so on. If I have repeated data values between data points, they each get their own bin. So if I had 577,911, I'd have 577,911. So I'd have two bins with 7 if that was the case. So each data point gets its own bin. And once I have this set up, actually all of my percentile questions are really easy to answer. I can ask maybe, for instance, what data value is at the 47th percentile. Well, I just find 47% on my number line here, and I see that that's in the bin belonging to the data value 8. And these, of course, come with the units of the original data. We just pulled them straight over as data values, so that would be 8 returns per day. I could ask the inverse question. What percentile is associated with, well, let's say the data value 9 returns per day. Well, I look at 9. I look at the data value 9. There's only one of them. And 9 spans the bin going from 60 to 80%. So I just average it. Or take the midpoint. I would say that 9 is at the 70th percentile. Now, one note that I talk quite a bit more about in the full lecture is this isn't a super nice one-to-one function. So if I said what percentile is associated with the data value 9, that's the 70th percentile. So what data value is at the 70th percentile? Well, I find 70%, that indicates 9, that's 9. Okay, I mean, that meshes. But what if instead of the 70th percentile, I ask for the 75th percentile or the 61st percentile? Well, those are also 9. There are a lot of percentiles that get associated with the data value 9 in this direction, but not in the other direction. In essence, what I have is a step function. So here's, what would this be? This would be percentile and data value. And I have something that goes like this. And so my problem is unfortunately somewhat ill-posed. If I give you a percentile, I can identify the data value with no problem. But if I give you a data value I'm interested in, there's a whole range of percentiles that get mapped to that data value. Which one should I choose? We choose the midpoint, the one that's in the middle of the inputs that get mapped to that output. Some books choose the left endpoint, some books choose the right endpoint. I think either of those is kind of a bad practice because, well, we talked quite a bit about making unbiased statistics as we get more and more data. If we were to, take a larger, now this is a population in this case, but if we were to think of it as a sample, if we were to take a larger sample, if we were to add to this sample, I would want my estimates to get closer and closer to the population parameter and not move around too much, right? So, but I don't think that's going to happen. If I always pick the left endpoint, I'm going to be biasing things to the left, or pick the right endpoint and biasing things to the right. So I think picking in the middle is the way to go. And again, I talk a lot more about this in the lecture, so we're not going to dig too deeply into this. There is a way that we can really kind of anchor on just this kind of midpoint here, more or less, and then connect the dots like this to make a one-to-one function, so that this answer is now unique in terms of this piecewise linear function. There is a way to do that. That's the kind of thing that Excel does. There are pluses and minuses to this. Number one, I mean, the main plus is we get a nice unique solution now. There's no ambiguity, but the only reason there's no ambiguity is because we chose to connect these points with a straight line. And why should we connect them with a straight line? Why not a curve? Right? There are lots of ways we can connect these points together. So there's still ambiguity. It's just that we settle the ambiguity at a different point in the process. So should we do linear interpolation like this? Should we do a more complicated interpolation like with splines? Should we not do interpolation at all? That's the route that we went. We said we're not going to do this interpolation idea at all. We're just going to accept the fact that there is a little bit of ambiguity, and we'll settle the ambiguity by basically taking the average of what the answers could be. So again, a lot more information in the lecture on this, but I think that's the main thing I want to point out here. There is also a supplement posted in the supplemental materials on Blackboard on chapter 3, like kind of going through a few more examples of this graphical approach, and giving you a couple of exercises you can work through, and then a separate document on the answers to those exercises. So if you want a little extra practice, you can go there for that on Blackboard in the supplemental materials folder in the chapter 3 subfolder. Okay, any questions so far? Okay, so moving on then to discuss skewness and outliers. Again, this was material that was also in those videos, so this should be review. This is, not meant to be the first viewing of this, but just kind of a reminder of what was covered. So definitely, I go a lot more into detail in that lecture. So far for skewness, we've had kind of two ways to assess the skewness of a data set. One way was basically graph it, make a histogram, and look at it and see if it looks skewed. That was pretty subjective. Different people could easily come to different conclusions based on the same data. We had something that was a little more objective. So we had, first pass was just the graph, the histogram. Does it look skewed? That would be maybe a histogram that I think most would agree looks right skewed. Outliers exist and fall to the right. In section 3.1, we saw, well, if we have skewness, then we would expect the measures of center, particularly mean, median, and mid-range, to line up a certain way. So therefore, we can say if the measures of center line up a certain way, then that provides at least some evidence in favor of skewedness. So for instance, if I had that the mid-range was much bigger than the mean, which was much bigger than the median is kind of the anchor, and the mid-range only looks at the extreme value, so it's affected the most by outliers. If I have outliers to the right, that should pull the mid-range up really high. So if I see that the mid-range is much higher than the mean, and that the mean is much higher than the median, then maybe I look at this and say, I think this is evidence of right skewedness. And for some reason, I can't write MD. MD, there we go. This was a little more objective. I mean, certainly whether they line up in this order or not is objective. But what does it mean for the mid-range to be a lot bigger than the mean, which is kind of what I'm trying to signify with this double inequality symbol here. Not just that it's, 1% bigger, but that it's a lot bigger, that it's getting pulled way off to the right. Or what does it mean for the mean to be a lot bigger than the median? Again, reasonable people could disagree on, some borderline cases. So a little more objective, still a little bit subjective. And this is where the Pearson coefficient of skewedness comes in. It gives us a completely objective measure. Now, people could argue, they could come up with a data set and say, I think this data set should be skewed right, but the Pearson coefficient says it's not skewed. Well, okay, fair enough. This is a completely objective measure. Does it mesh with what the type of things that we expect it to do? That's a different question, but it's at least completely objective. The Pearson coefficient is 3 times the mean minus the median over the standard deviation. And we say the following, we say if the Pearson coefficient is bigger than +1, that's evidence of right skewedness. The standard deviation is always positive. So really, if we're looking at mean minus median, Pearson coefficient being strongly positive would mean that the mean is bigger than the median, as we'd expect in right skewedness. If the Pearson coefficient is less than -1, in other words, if the mean is a lot smaller than the median, that's evidence of left skewedness. And otherwise, if the Pearson coefficient is between -1 and 1, and probably the best way to say this is that that represents a lack of evidence of skewedness. I probably wouldn't say like that it's evidence of symmetry, but I would probably say it's a lack of evidence of skewedness. Now, what's the Pearson coefficient really saying? I could rewrite it. I could rewrite it by putting that 3 on the bottom. It's the mean minus the median over 1/3 of a standard deviation. And I'm asking, how does this compare to, roughly speaking, 1 or -1? So really what I'm asking is, how does the difference between the mean and the median compare to 1/3 of a standard deviation? Really what I'm saying is, if the mean is more than 1/3 of a standard deviation above the median, then there's evidence of right skewedness. If it's more than 1/3 of a standard deviation below the median, then that's evidence of left skewedness. And if it's not more than 1/3 of a standard deviation away from the median, then the two are close enough that there's a lack of evidence of skewedness. So what does it mean to be, for the, say, the mean to be much bigger than the median, or for the mean to be much smaller than the median? At least according to Pearson's coefficient of skewness, much bigger or much smaller means more than 1/3 of a standard deviation away. So that's the claim being made by the Pearson coefficient of skewness. This is completely objective in the sense that if you hand 100 people that know what they're doing and can do the computation right, if you hand them all the same data set, they would all come up with the same answer. Evidence of right skewedness, evidence of left skewedness, or lack of evidence of skewedness for that same data set. There's no gray area here. Now, would a person look at the data set, look at the histogram, look at how the measure of center line up, and look at the Pearson coefficient, and would they think that all those things agree? Well, that's subjective, right? Maybe I feel like I think this is a right skewed data set, but the Pearson coefficient comes out to be 0.95. And it says, lack of evidence of skewedness. It doesn't quite pass that boundary of +1. You can disagree with the conclusion of the Pearson coefficient of skewedness in light of, say, the surrounding the other data, the other characteristics of the data set. But the Pearson coefficient of skewedness itself and the claims that it makes are completely objective. So there are other ways to define skewedness. So there are more complicated ways. There are ways in mathematical statistics to define skewedness, and right there might be a little bit of friction. Maybe this definition says the data set has this much skewedness, and this other definition says that it's not skewed or something. Or so this isn't a cut and dry kind of question to answer. Kind of similar to how, like, what's the typical data point look like isn't a cut and dry question to answer. It requires maybe some choices to be made along the way, either a choice of what loss function is appropriate here, or a choice of, do I want to report the median if I suspect there's skewedness? Is that going to be a more appropriate measure to report than, say, the mean, maybe, which might get pulled around by a couple of outliers? Or in other circumstances, even if there are outliers, we might still want to report the mean for a particular reason. So statistics is a little bit less black and white than, say, algebra or calculus or something like that. There's almost always a decision point that has to be made from kind of the human side, a judgment call that needs to be made somewhere along the line. Sometimes we pretend that things are completely objective, like here, but really all that we've done is push that judgment call earlier. We've said, I'm choosing to use the Pearson coefficient of skewedness as essentially my definition of skewedness, but that was a choice that had to be made. Why did I make that choice instead of choosing a different measure? So statistics is a lot more flexible than a lot of other math fields. Any questions so far? Okay, and then the two-standard deviation method for identifying outliers. One thing to remember is if a data set is skewed, to have a skewed data set, say it's right skewed, that means we have outliers to the right. So if a data set is skewed, we know there must exist at least one outlier. So if skewed, at least one outlier. However, if let's say I do a Pearson coefficient of skewedness, it comes up to be 1.5. I look at my data set and it looks like this. Well, in that case, at least according to the Pearson coefficient of skewedness's definition, if I say the data set is right skewed, I know that this rightmost data point, this data point with the highest value, has to be an outlier, at least according to this definition. But what I don't know, what about this next one? It kind of looks like an outlier, but is it? What about this one there? Is that an outlier? Even if I say that I'm right skewed, I know that there's one outlier, but are there more? Is my second highest data value or my third highest data value, are they high enough to be outliers? I don't know. The notion of skewedness doesn't tell me anything about that. On the other hand, if we're not skewed, we really can't say anything about outliers, because I could be not skewed by having outliers to the right, but balanced by outliers to the left. I could have outliers on both sides. Maybe all of these are outliers. So just looking at skewedness, or determining whether I have left skewedness, right skewedness, or seemingly lack of skewedness, really is not enough to tell me much at all about the outliers. The only thing I can really say is if I'm skewed one direction, then my data value that is the furthest in that direction ought to be an outlier. But that's really all I can say. So my goal now is to come up with a method for identifying outliers that looks at each individual data point and can answer the question for each individual data point, is this data point or is this value an outlier or not? So my goal is to be able to go through and look at each of these, and for each of them ask, is this an outlier or not? And in practice, what I'll do is I'll create a lower bound and an upper bound, and I'll say, anything in between these bounds are not outliers, and anything to the right of the upper bound or to the left of the lower bound, anything that falls in either of those extremes is an outlier. So then I would say yes for this one, yes for this one, and yes for this one. But no, none of these are outliers if that was what my picture looked like. So my goal is to come up with such lower and upper bounds using some method. As you might guess, we have a uh, fairly ill-posed problem here, fairly can't think of the word I'm trying to think of, but the notion of outliers is imprecise. It's just a data value that doesn't really fit in with the rest of the data. So we have a couple of ways to answer this. We have many ways to answer this, but a couple that we'll talk about. The two standard deviation method, which is kind of a quick and dirty method that works most of the time pretty well. But it has a few downfalls, or well, maybe one particular downfall. So we might want to use something that doesn't have that downfall, and that's where the 1.5 IQR method, or just sometimes it's just called the IQR method, comes into play. So the two standard deviation method, easy to understand, easy to apply, used in a lot of places, especially like labs. If you've done a chemistry lab or a physics lab where you have to get a bunch of data, often they'll apply something like the two standard deviation method to look for outliers and throw those out of the data set, mainly because it's quick and easy to apply. So what is the two standard deviation method? It says any data point with value more than two standard deviations from the mean is an outlier. Or if the absolute value of the z-score is bigger than 2 for that data value, we call it an outlier. So what do? We construct a lower bound of, say, x bar minus 2 standard deviations, and an upper bound of the mean plus 2 standard deviations. Between L and U, between the lower and upper bound, all of those data values are non-outliers. They're close enough to the mean that we say they're not outliers. Anything that's below L, any data point that has a value less than L or greater than U, we would say that those do represent outliers. So let's come up here and look at the Ashley and Brandon data. Hopefully I can copy this down and it doesn't blow everything up. Good. It's always a little bit of a gamble. Feels like you're going to the casino when you copy and paste something on Microsoft. Although it seems like it's gotten a lot better just in the last couple years. I don't know if it's just me being getting better at knowing what I can copy and paste reliably, or if there have been improvements in the background. But it used to be the case, like you copy something down and it would throw everything off in the whole document. But seems like it's gotten better. So I will give Microsoft credit where it's due. I've heard that that they're reopening one of the 3 Mile Island reactors that famously melt. Well, one of the reactors, probably not the one they're opening, melted down. I don't know, many decades ago, and they're reopening one of the 3 Mile Island reactors to sell the energy to Microsoft for running AI or something like that. So I made a joke on one of the Facebook posts about somebody says, "Oh, well, they're upgrading it. Like it's not a big deal. They're updating everything." And I said, "Yeah, because Microsoft is known for their stable updates." So obviously it's not Microsoft doing the reactor updates, but um, anyway. Um, okay, so let's investigate each of the Ashley and Brandon data sets to see whether we see any outliers in either of them. So for the Ashley data set, again, my idea is I want to construct a lower and an upper bound that represent kind of the minimal and maximal non-outlier data values. So Ashley's lower bound is going to be her mean minus twice her standard deviation. This is a population, so I guess we'd use mu and sigma instead, but same idea. The mean of 8 minus 2 standard deviations, 2 times 2, 8 minus 4 is 4. And her upper bound is going to be the same thing, just with a plus, going 2 standard deviations above the mean. 8 plus 4 is 12. So do I see any data points with value either less than 4, less than the lower bound, or bigger than 12? No, the data point with the lowest value has value 5 and the highest value 11. No. So no outliers in the Ashley data. What about the Brandon data? We can do something similar. It's going to, the Brandon data set's going to have a different lower and upper bound because it has, even though it has the same mean, it has a different standard deviation. So the lower bound is going to be the mean of 8 minus 2 standard deviations, but now a standard deviation is 4 returns per day. 8 minus 8 is 0. And 8 plus 2 times 4, 8 plus, or mean plus 2 standard deviations is 16. So actually no outliers in the Brandon data set either. I mean, the 3 and the 14 are certainly more spread out than Ashley's numbers, but kind of the whole data set is spread out, right? It's like everything is kind of a little bit more spread out in the Brandon data. It's not like Brandon has, 5, 7, 8, 9, 20, where like kind of everything's clustered together, just like the Ashley data, except for this one that's way off to the side. It's like everything is a little more spread out in the Brandon data. So this higher standard deviation expands the range of kind of reasonable values for the Brandon data. Ashley had a tighter range for kind of the reasonable values because her standard deviation was lower. Just in general, her data set's less variable. So it would take less of a deviation for a data point to be considered an outlier because much of her data is clustered very closely together, where Brandon's a little more spread out in general, which is reflected in his bigger standard deviation. Okay, so that's a pretty quick and easy test, right? Um, we either we go to Excel, let's say, and compute mean and standard deviation for our data set, and we either construct a lower and upper bound and search for outliers that way, or we could go ahead and next to each data point, we could construct the z-score for its value. That's another way that we can think about this is if the z-score is less than -2 or bigger than +2, we could search for any z-scores that are less than -2 or bigger than +2. So we could actually even have Excel do essentially all of the lifting for us if we constructed a z-score. And then we didn't talk about this, so we could do like a conditional formatting thing and just say color the cell red or something if the value is more than 2 in absolute value. Okay, so This is pretty quick and easy, especially if we're not doing, standard deviation by hand. It's used in a lot of, like I said, labs and things like that because it's pretty easy to apply. What is a downfall of this? Well, let's suppose we have kind of a nice little data set here that looks like this. So this data set is going to have a mean, maybe like this, and it's going to have a standard deviation that's maybe something like that. That's like that big of an interval on the real line. And then if I go, two standard deviations to the right and two to the left, it's going to have maybe a lower bound and an upper bound that look like that. You go a little further to the right, like that. And so I have no outliers. So I've gone two standard deviations to the left of the mean, two standard deviations to the right of the mean. Now I'm going to kind of cheat here. I'm just going to, again, cross my fingers and hope that I can just copy this down and it won't mess everything up. And it looks like I need a little more room here. All right. Try that again. That wasn't a Microsoft issue. That was just me not knowing how much room I needed issue. Okay. I think everything worked well there. Okay, now let's say that I stick in a data value or a data point with value way off to the right. So according to the kind of previous value of standard deviation and the previous value of X bar, this is to the right of you, it's clearly an outlier. But here's kind of the issue. I stuck in this red data point now, this data value way off to the right. That's actually part of the data set, right? So my X bar from just this data is not going to be the same. It's not going to stay the same. In fact, my X bar is going to chase that outlier. When I put this outlier in off to the right, that's going to pull my X bar to the right. That's going to have the effect of pulling my lower bound, but also importantly, my upper bound a little further to the right. But not just that. We know that outliers have an outsized effect on standard deviation. So in the presence of this outlier, my standard deviation now gets a lot bigger. It used to be this size here, now it's significantly bigger. And I start counting to the right two standard deviations from the new X bar. So it might actually be the case that, let me actually do this one in red too. It might actually be the case that my upper bound doesn't even indicate this as an outlier. Maybe this ends up falling just inside my upper bound, even though it's pretty clearly an outlier, right? What is the problem? Well, the problem is that the mean is affected by outliers, the very thing that it's trying to help identify. And the standard deviation is tremendously affected by outliers. Again, the very thing that it's trying to identify. In the presence of outliers, the standard deviation gets much bigger, making my lowered upper bound interval much wider. Just from the presence of a single outlier, it gets much wider. Not just because the overall data is more spread out, but just that one outlier pushes my standard deviation up, makes the interval from L to U much wider. And if I have skewedness, if I have outliers more on one side, my X bar is like chasing the outliers. So when I have an outlier on one side, my upper bound, say on the right side, my upper bound is going to actually chase that outlier. Neither X bar nor sigma are robust to outliers. When an outlier enters the picture, both of them are changed significantly or substantially. And the tendency for both of them is to kind of chase that outlier to make things that would have been considered outliers no longer considered outliers. Right? So my X bar moves in the direction of the outlier and my standard deviation gets bigger, pushing my upper bound in this case more in the direction of the outlier as well. So that's kind of the issue here is I would like if I'm going to search for outliers, I don't want the method of searching for outliers to be heavily influenced by outliers. I want the method to kind of give me, solid like anchor points that I can rely on, and then I can measure where my data values fall relative to those like anchor points. And if I have an outlier or don't have an outlier, those points should stay basically the same for a very similar data set. Right here, we have a very similar data set. We just added in one outlier, and that kind of changed the entire landscape of the method that I'm using to search for outliers. So the 1.5 IQR method for identifying outliers tries to solve this problem. This is what I would say is probably the most standard way for identifying outliers. If you go to a statistics package like R or like some of the packages in Python, it's just standard method of saying whether a data point's an outlier or not is probably going to be 1.5 IQR. So what's the idea here? The idea here, oh, and I want to quickly remind us, I forgot to mention this up above, in percentiles, we have the idea of quartiles. Q1 is the 25th percentile, and Q3 is the 75th percentile. Q2 is the median, is the 50th percentile. So I know that I mentioned this in the lecture, but just as a reminder, these quartiles are what we're going to use in the IQR method. Okay, so the IQR method, what's the idea here? So we start by computing the IQR, the inner quartile range. So the IQR is Q3 minus Q1. It's the distance spanned from the first quartile to the third quartile. So if I were to have, say, a data set that looked like this, and maybe I have Q1, the 25th percentile here, and maybe Q3, the 75th percentile there, this distance would be the IQR. So it's a swath of the real line, kind of like standard deviation. It's kind of like standard deviation. Note that the first and third quartiles, or percentiles in general, have units of the original data. So their difference also has units of the original data. So IQR has units of the original data. IQR is kind of a measure of variation. It's a little bit like standard deviation, except that standard deviation, remember, is heavily affected by the presence of outliers. If there is an outlier, standard deviation shoots way up. But IQR, I mean, if I have a right outlier, if I take this data point and push it all the way over there, the IQR just, or the third quartile just chops it off. Right? My largest data value is probably not at the 75th percentile, or else I have to have a very small n for my data set. My largest data value just gets chopped off. It just gets ignored by the 75th percentile. Whether it's a little bigger or a whole lot bigger, it's just the first one to go. Same with the 25th percentile. If I had a big outlier on the left, I don't really care about that value because that just gets ignored, right? Up here, when I'm looking at my bins, I don't care if this is 11 or 11,000, if Ashley had some kind of, stellar day where she drank 20 cups of coffee and got 11,000 returns done. What's the 75th percentile? It's still 9. I don't care whether this is 11 or 11,000 or 9.01. We just ignore whatever's in that bin. The value gets completely ignored. That's our 75th percentile, regardless of what falls to the right of it. And similarly with the 25th percentile, it's going to be 7, whether this is 5 or 0 or negative 5 million. That 25th percentile is still 7. We just ignore everything to the left of the 25th percentile, all those lower data values. So the only way that we would start kind of chipping in, so to speak, to the IQR with outliers is if more than 25% of our data were outliers. If more than 25% of your data are outliers, it's kind of hard to call them outliers then, right? Like, how do you say that this data point doesn't fit in with the rest of the data when like 25% of your data points don't fit in with the rest of the data, supposedly? That doesn't make a whole lot of sense. Okay, so that's our interquartile range. It's a measure of variation. It's kind of the stand-in for what the standard deviation is kind of doing up here. It's giving a measure of kind of the size of the variability of the problem, but it's robust to outliers. If we stick some outliers in there, Q3 and Q1 don't change at all. They act like the median. They're just like anchors that sit there. So what's the 1.5 IQR method then? Well, I construct a lower and an upper bound. Now, if I really wanted to mirror this up here, I would do, instead of like mean plus or minus 2 standard deviations, I might do something like median plus or minus 2 IQRs. I have to be completely honest with you. I've looked into this. I don't know why they don't do that. I the person who kind of like came up with this 1.5 IQR idea, I think it was John Tukey. Very smart statistician, much smarter than me. So I'm sure he had a reason. I'm sure that he would have thought of that and said, oh, why don't I do it this way? And then decided to do it this way instead. I've looked into it. I don't know why they do this. I've wanted to post on like the stats stack exchange or something and just keep forgetting to and be like, hey, does anybody know why they do it this way? So what we do instead is we start with Q3 as the kind of anchor point for our upper bound, and we add 1.5 IQRs. And for our lower bound, we start with Q1 and subtract 1.5 IQRs. So what am I doing? I have Q1 to Q3. The distance between them, that's a span of 1 IQR. If I go up to my upper bound, I'm going 1.5 IQRs to the right of Q3. And if I go down to my lower bound, I'm going 1.5 IQRs to the left of Q1. I have a span of 4 IQRs from lower to upper bound. But wait, what did I have up here? If I look at my 2 standard deviation method, I have a span of 4 standard deviations. And my range rule of thumb said that like the range, kind of the lower to upper bound minus lower bound, is approximately 4 standard deviations. So it's kind of like my range, excluding outliers, looks like 4 standard deviations or 4 measures of variation. And here I'm choosing to use IQR as my measure of variation. I want to cut a 4 measure variation swath out of the real line and consider those normal values, normal data values, and things that are outside of there, I want to consider outliers. It's the same basic idea. I cut a 4 IQR swath or a 4 standard deviation swath out of the real line. But both my measure variation, IQR, and my kind of measure of center, these Q1 and Q3s, none of these are affected by outliers. These are all robust to outliers. If I take this data value and push it way over to here, nothing changes. Q1 doesn't change, Q3 doesn't change, the IQR doesn't change, this lower and upper bound doesn't change, right? Where when I did that down here with the 2 standard deviations, the standard deviation increased substantially and X bar kind of chased my outlier. So my upper bound moved in the direction of my outlier pretty substantially. So that's why the 1.5 IQR method is in some sense better. It's robust to outliers. Let's look at the Ashley and Brandon data and investigate them for outliers using the 1.5 IQR method. And then we'll do a couple examples on Excel. So Ashley's data, I see that Q1 or the 25th percentile is going to be 7. And I see the Q3, the 75th percentile is going to be 9. The IQR, 9 minus 7 or 2. So kind of my measure of variation, so to speak, here is 2 units or 2 returns per day. 1.5 IQRs are just 1.5 times this number gives me 3. And then my lower and upper bound are constructed by taking Q1 minus 3, 7 minus 3, and Q3 plus 3, 9 plus 3. So 4 to 12. And interestingly, for the Ashley data, we actually see we happen to get the same bounds in both cases, the standard deviation method and the IQR method. No outliers. But we know that Ashley's data set is kind of very well behaved. It's nice and symmetric. We kind of, intuitively guess that there are no outliers. So that's not the kind of situation where we expect there to be a big discrepancy between the 1.5 IQR method and the 2 standard deviation method. Brandon, I don't know. I mean, maybe his 14 is a little high or his 3 is a little low. Doesn't seem too terrible though. But let's check. So similar to Ashley, Brandon also has 5 data points. His Q3 and his Q1 are going to be the associated, second and fourth smallest data points, just like Ashley's. So 5 to 11, that's kind of covering up the 5. So 5 and 11 for the 2 quartiles for Brandon. Brandon's IQR is 11 minus 5, or 6 returns per day. That's his measure of variation. In this case, it's 3 times as large as Ashley's IQR. One and a half IQR is 1.5 times 6 is 9. We construct a lower and upper bound. as Q1 minus 1.5 IQRs, 5 minus 9, well, that's a -4, and an upper bound of Q3 plus 1.5 IQRs, 11 plus 9 is 20. Brandon's data set's more variable, but this 3 is not less than -4. The 14 is not bigger than 20. There are no outliers in Brandon's data set either. His is more variable, but it's not like one of these data points really doesn't fit in with all the others. It's just that kind of everything is a little more spread out. Okay, so let's jump over to our Excel spreadsheet, same one that we've been working with. And let's do a couple of things. Let's compute the Pearson coefficient of skewedness for each of these. And then let's jump over to a different sheet after that, and we'll look at evaluating a couple of data sets for outliers. So our Pearson coefficient is equals 3 times mean minus median. I need parentheses here. Parentheses, mean minus median. I'll just select those two cells. And my parentheses, and divide by the standard deviation. So again, oops. So again, I want Excel to do a computation for me. So I start with equals. I know that my Pearson coefficient of skewness, the definition, we're going back a little ways. Let me bring that back up. 3 times mean minus median over standard deviation. So 3 times parentheses, click on the cell where we computed the mean before, subtract the cell where we computed the median, and parentheses, and then divide by the cell where we computed the standard deviation. We don't have to type in the mean and or average and median and standard deviation, stdv.p, all those again. We can just refer to the cells where we had already computed those. And of course, Ashley's mean and median are exactly the same. The Pearson coefficient is 0. Mean minus median is 0. There's a lack of evidence of skewedness for Ashley's data. If we just click on that bottom right-hand corner and drag over, we see that copies all of these cells over. We still have that kind of relative referencing going on. It copies everything over by 1. And now we get the same answer or the same measure for the Brandon data. Brandon's Pearson coefficient is 0.75. A little bigger than 0, but it's not bigger than +1. It's not high enough to be evidence of right skewedness. The mean of 8 is a little bigger than 7. Even the mid-range is a little bigger than the mean, right? But the Pearson coefficient says they're not far enough apart for us to consider this evidence of right skewedness. If we come over to the salary data, well, this is the one where we have the 100 that I think, we look at most of the data and we say it's like 25 to 30 for 5 of the 7 data points. And we have this one salary of 100, another salary of 55. This is something that we might have suspected was a bit right skewed. Mean of 42, median of 28, even a mid-range of 62.5. We're pretty suspicious at this point. And then we look at the Pearson coefficient and it's 1.5, 1.5. Definitely bigger than 1. So we'd say there's some evidence of right skewedness in this salary data. Now, one kind of minor caveat. We have mentioned in the past that that sample size is important to keep in the back of our minds. A sample of size 5 or 7, that's a pretty small sample size. So would I want to really draw really firm and strong conclusions on such a small sample? Probably not. But we're dealing with small samples here so that we can work through things by hand. So there is a caveat to all of this, but it certainly seems from the Pearson coefficient, the way that the measures of center line up, and just kind of looking at the data, it certainly seems that there is some evidence of right skewedness here, and that would suggest to us that maybe this value of 100 up here is an outlier. So if I call this data set right skewed, I'm implying that 100 is an outlier. But is 55 an outlier? I don't know, right? Uh, I'm not sure. The Pearson coefficient, even if we buy it and we say yes, right skewed, all that really guarantees, in a sense, is that 100 is an outlier. Doesn't really say anything about 55 or any other number. So let's go across our tabs at the bottom here. If you didn't realize, there's a spreadsheet in Excel, but if you go to the bottom where it says datasets class, you can go over to like datasets class done. This is just with some of these computations put in here. Or ETF example. This is a different example. I think I'm going to skip it due to time. Just the interesting little finance thing. And then we can jump over to outlier data sets. That's where we're going to spend probably the rest of our time today. And we'll probably pick up with chapter 4 next time. Okay, so in this tab, outlier data sets, we have a different worksheet with some different data. We have 2 different data sets here. One of them is Challenger mission flight times in minutes. And of course, there was the one Challenger mission where the uh, where it exploded right after takeoff. So I think we would all pretty much agree. I don't think there's much gray area here that one is an outlier. All of these other numbers are in like the thousands or tens of thousands, right in the ballpark of 10,000. And then we have the number 1. I think we'd all agree that's an outlier. Let's see if our tests pick that up and to what degree they do and so on. Then let's look at something that's a little less clear, car crash head injury criterion numbers, and do the same thing, right? It's a little less clear whether we have any outliers here or not. Okay, so let's start off by just computing kind of our basic statistics here. So standard deviation, and we'll call this a sample. So we'll put parentheses S there. And let me actually I always forget that escape, gets rid of what I typed into the cell, but it also brings up the zoom information panel. So every time I hit escape, I get a little bit surprised when it doesn't do what I expect it to do. And okay, so let's compute standard deviation, but let's go through and give this data set a name. So I'll select it, and maybe I'll call it CHALL, Challenger. Or why not just call it Challenger? We can just tab and autocomplete, so we'll just name it Challenger. I did that by selecting my data set, coming up here above this like A column and just clicking in the name box and renaming it. So I want a sample standard deviation. I start with equals, tell Excel I want to compute something, stdev.s for sample standard deviation. What I want to take the sample standard deviation of, the Challenger data, start typing it in, and then just tab to autocomplete. That looks like the right data, and the parentheses, and hit enter. And we see the standard deviation about 3,400, right? Mostly from this one. If I made this, 8,500 or something, kind of just putting it in the middle there, we see that standard deviation is cut in half, cut more than in half. The range, that's the maximum minus the minimum, or the range is 11,843, right? Essentially just the maximum because the minimum is so close to 0. The mid-range, our measure of center that only looks at the extremes. I want the average of the max and min, so I could do like max of this minus min of this. I could also just cheat and do. I know these are in order, so I could just identify the individual cells that I want and save myself quite a bit of typing. I know that I've put them in order. Now I do have to remember that if I were to say do a scenario analysis and go in and say, well, what if this 1 was, instead of being a 1, if it was like 10,000, well, now my mid-range isn't going to be right, right? Um, so I'm averaging this cell and that cell, but I did it in a bit of a hackish way, so it's not going to update super nicely if I go changing things around to look at different scenarios. I can take the average of the challenger data for the mean or the average, and I can find its median. And I do note that the mid-range, the one most affected by outliers, is about 6,000. That does seem to be quite a bit lower than the roughly 9,000 for the average. And that 9,000 for the average does seem to be a bit lower than the median of about 10,000. So 10,000 down to 9,000, that's a change of, say, roughly 10%. 9,000 down to 6,000 is a change of roughly 30%. So I do see that my measures of center kind of line up in a direction indicating some left skewedness. My Pearson coefficient, well, 3 times parentheses mean minus median divided by standard deviation. Actually, my Pearson coefficient is only negative 0.95. Doesn't quite cross the barrier of -1. So my Pearson coefficient maybe indicates lack of left skewedness, lack of skewedness at all. My measures of center probably indicate some left skewedness. Having that left outlier maybe makes me feel like left skewedness. It's maybe a little bit unclear, right? I would have to make a judgment call here. Do I stick really hard and fast to that? Well, Pearson coefficient is not less than -1. So we say lack of evidence of skewedness, or do I take, the whole picture into account? For my 2 standard deviation test, I've already put the formulas in here. I have my mean minus 2 standard deviations and my mean plus 2 standard deviations. And we see this takes me from about 2,000 on the lower bound to about 16,000 on the upper bound. There are no data points above 15,900, but we do have one data point that's below 2,000, this number 1 here, the one that blew up, and that is our one and only outlier according to the 2 standard deviation test. Okay, and then lastly, let's do the 1.5 IQR method. We need to figure out our quartiles, our 25th and 75th percentiles. Excel does have a function for percentile, but as I kind of mentioned, wherever it was, as I kind of mentioned over here, it kind of does this kind of interpolation kind of thing, and that's not really how we're approaching it. So just so that we get consistent answers, let's just figure out which of these data points we're going to call Q1 and which one we're going to call Q3, the 25th and 75th percentile. I see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. So if I think I want to split 0 to 100% into 10 bins, the first bin is going to be 0 to 10%. That's going to be the bin for the number 1. 7224 is going to be in the second bin from 10 to 20%. 8709 in the bin from 20 to 30%. That's where 25% lies. This will be Q1, our first quartile. To get Q3, we can either use symmetry. 3 up from the bottom is Q1, so 3 down from the top has to be Q3. Or we could start up here and say, okay, 11844 is going to be the 90% to 100% bin. I have 10 bins from 0 to 100%. They each get 10 percentage points, so I can count down from the top, 90 to 100, 80 to 90, 70 to 80, and that's where 75 lies, in the 70 to 80 bin. So Q1 is going to be this number, and Q3, this number. My IQR is their difference, 11,445 minus 8,709, or about 2,700 for my IQR. Note that 2700 is quite a bit smaller than 3400, my standard deviation, because the IQR is not being affected by this outlier, right? The IQR only cares about these two numbers, 8700 and 11445. It just completely ignores this one. If this one was, um, 7500 instead, my standard deviation changes a whole lot. My IQR is exactly the same. 1.5 IQRs is 1.5 of these. That's how far we're going to go to the right of Q3 and to the left of Q1. And my lower bound is Q1 minus 1.5 IQRs. And my upper bound is Q3 plus 1.5 IQRs. Yep. Yeah. We're going to go through a second one here as well. So to find our 25th and 75th percentiles, we just did the kind of 0 to 10, 10 to 20, 20 to 30 bins. So the 25th percentile is in the 20 to 30 bin, and then symmetry just gives us the third quartile. The IQR is the difference between the third quartile and the first quartile. So G8 minus G7, or 11,445 minus 8,709. That gives us 2736 for our IQR, basically our measure of variation we're using here. 1.5 IQRs is just 1.5 times that IQR number. And then my lower and upper bounds are Q1 minus 1.5 IQRs and Q3 plus 1.5 IQR cell. And we notice our upper bound actually comes out pretty similar to the two standard deviation test, 15,549. No high outliers. Our lower bound turns out to be 4605, substantially higher than the lower bound for the two standard deviation tests. We have still indicating the presence of one low outlier, this one down here. But note that this one low outlier caused the lower bound of the two standard deviation tests to kind of chase it, so to speak. But the 1.5 IQR method stayed about the same. So if I brought this up to maybe 4,500, let's see what happens. Okay. Need to go a little bit further. Oh, not that one. So up to 4,800. My 1.5 IQR method now is, I suppose, not calling this an outlier. And my two standard deviation test is calling it an outlier. So we can get disagreement between the two. We also note that characteristic that when we do have an outlier, it doesn't really affect the 1.5 IQR method. It's still the same 4,600, but my two standard deviation test lower bound is much lower than it would be otherwise. Okay, and then let's go through. So there is another sheet on here with all of this completed. But let's just go through the 1.5 IQR bit for the car crash head injury criterion. So here I have 7 data points. So I need to split 0 to 100% into 7 equal sized bins. Each one's going to be about 14%. 1/7 is about 14%. So 0% to 14%, that's the first bin, that's 326. 14 to 28%, that's the second bin. And the 25th percentile falls in that second bin from 14 to 28%. And analogously, the second down from the top is going to be Q3. Or we could say that 100% down to 86%, that 14 percentage points, will be the bin allocated to the highest number, 544. So that's 100% down to 86%. And then 86% down to 72% will be the percentage point, the percentages, percentiles allocated to 520. And 75% falls in that bin of 72% to 86%. That's Q3. So Q1 and Q3 are those two numbers. The IQR is the difference. Q3 minus Q1. 1.5 IQRs. We don't have to compute this separately. We could compute it as part of the lower and upper bounds, but just computing it here so that we can kind of see it a little more explicitly. And then for my lower bound, I take Q1 minus 1.5 IQRs. And for my upper bound, Q3 plus 1.5 IQRs. So my 1.5 IQR test gives lower and upper bounds of 110 and 766. I don't see any data points with value less than 110 or bigger than 766. No outliers. And if we take a quick peek at these answers, we have no low or high outliers in the two-standard deviation test. And here we have our mid-range is the largest, our mean is in the middle, and the median is the smallest, maybe indicating a little bit of right skewedness or maybe a right outlier. But if we look at the sizes, like the mid-range to the mean is only 5 units difference on a scale of 400, like 1% difference. And the mean to the median is only like, what, 35% difference or so, maybe, sorry, 35 units difference, maybe 10% difference. I don't think there are any outliers here, even though it turns out the Pearson coefficient is a little bigger than 1. We get a little bit of disagreement between our Pearson coefficient, suggesting some right skewedness, at least one high outlier, versus our tests for outliers, indicating no outlier. A little bit of disagreement there, right? This would be kind of a gray area. We'd have to take all of the available information into account. And for whatever reason, if we're trying to decide, should I call this an outlier and get rid of it from my data before I do any further processing, I would have to make that decision qualitatively. So not a really clear-cut answer on this one. But I would probably lean more towards being no outliers because my more reliable test says no outliers rather than my ones that are more affected by the presence of outliers and other kind of strange things like that affect standard deviation and so on. I probably would rely on something like this a little less and something like this a little more. I'd probably say no outliers. But another reasonable person could say they think that there is a right outlier because of the Pearson coefficient. All right, let me end the recording.